as you probably know, this is, well, you know, it turns out different people have different opinions. In my opinion, deep networks is the most exciting thing to happen to machine learning in the last decade. And so we're going to start a sequence of 3 lectures on this topic. And today we're going to see how they're trained and jump right in. So let me motivate this a little. We like logistic regression. That's why we spent a few lectures on it. But there are some problems where logistic regression doesn't work so well. So for example, if I wanted to train, of course, logistic regression is simply a way of training a system so that it can predict the probability of some variable y from a bunch of other features that might be continuous or discrete. So if we used it, for example, for image recognition, we could try to train a system that, for example, predicts the probability that the input picture contains Hillary Clinton, given all of the different pixel values, thousands of pixel values as the x sub 1 through x sub 10,000. Then if you think this through, you realize it's really not going to work so great. For one thing, if we define our x sub 1 as this first top left pixel, and our x sub 2 is something else, another pixel, if each of our x sub i's are fixed pixels in the image, then we have problems like here's Hillary in this part of the picture, but over here she's in a different part of the picture. And so even if we learn some dependency of y on individual x sub I, that's not going to be sufficient in the case of photographs. Furthermore, there are an awful lot of pixels. And anyway, if you try this, you probably wouldn't try this, but if you did, it really won't work very well. And so at the heart of the problem is really that these individual pixels are not really the right features to be using if we're going to train logistic regression. And so for many years, computer vision researchers have looked at the question of what are the features that we should use for classifying images. And so, you know, maybe we should have some low-level feature extractors that we write, for example, edge detectors, or color blotches, something that looks at regions of similar color and carves those out and builds some x sub i's that correspond to where is this blotch of color and how big is it, what are the red, green, blue values of it, and so forth. Or even maybe face features, if we could write an x sub I function that would extract face-like things. And people in computer vision worked for many years to come up with the right set of features. Around the year 2010, the most popular set of features is something called SIFT. I'm not even sure what it stands for anymore. Maybe what? Does anybody know? Okay, scale invariant, FT, feature something. Okay. Scale invariant features. So anyway, this is how computer vision research was going. But it turns out that deep networks are a way of learning those features automatically. That's why, one way to look at why deep networks have become so important in machine learning. For years, people manually tried to come up with these features. But now, instead, we just give a deep network the individual pixel values, and we count on it to learn the features. The result of that has been rather dramatic. On the standard set of computer vision test data, which is called ImageNet, In 2010, the best computer program had about a 30% error rate, and today it's down below 5%, which 5% turns out to be about the human error rate at recognizing objects like these kinds of things in this particular set of data. So, and what's remarkable about it is that even though here in 2010, these state-of-the-art systems were based on SIFT features and other manually developed low-level processing, pre-processing of the image. These systems are literally based on inputting the pixel values of the image and not even trying to human engineer the features. So that's one way to think about why neural nets are so important. So in general, here's a way to characterize them. They're another function approximation algorithm, just like the ones we've talked about, decision trees, naive Bayes, logistic regression. We're trying to learn a function from some input x to an output y. X and y might both be continuous or discrete, or a vector of continuous and discrete variables. And we represent the function by a network of computational units, which are in usually a fixed network structure, but each of those units can contain one or more parameters that get trained as part of the overall training of the network. And there can be many millions of parameters, in fact. Okay, so the net effect of that is that these networks can learn highly nonlinear functions. Remember when we talked about logistic regression, we pointed out that its decision surface, the surface that separates regions of x1 through xn, where it's going to say the probability that y equals 1 is greater than a half versus less than a half, is a linear decision surface in the case of logistic regression. But here I'm showing you a very nonlinear decision surface. This is for actually a very early vintage neural network for speech recognition. In fact, this network was trained just to figure out the vowel sound. So the input is two frequency bands, F2 and F1, characterizing the input speech signal from the microphone. So these are two real valued inputs. And the output is one of, I guess, 10 different vowel sounds that are represented. And so is it the vowel that you hear if I say the word head, or hid, or hooed, or hood? And you get the idea. So each of those has a slightly different vowel sound. And here's a neural network that was trained, given two frequency components of the input signal from the microphone, to predict which of those it is. And the output here was coded. Basically, you can think of the two inputs here as real valued numbers. And the outputs here were trained to be either a 1 or a 0, where the idea is if we had a training example where the correct output is I, as in hid, then we would code that as 0, 1, 0, 0, 0, 0, 0, 0, all zeros and a single 1. Some people call that a one-hot vector encoding of a label. You'll hear that term one-hot vector encoding several places in the literature if you start reading about deep networks. But that's the idea. And so what this plot over here is showing is if we plot all possible inputs, at least in this range for F2 and F1, then what are the regions where this trained network will predict that the output vowel is, let's see, plus means hod, ha-ah, hod. So if it's over here, all these pluses, this whole region of F1, F2 space would be labeled by this output network as the vowel ah. Whereas this one, which is the X's, would be ah. So you can see, and each of these points, in fact, is a particular example. And you can see that these regions are not perfectly labeling every example, but by and large, they're getting it right. So the important thing about this figure, the reason I bring it up, is that it gives you an idea of how very dramatically nonlinear the decision surface can be. This is the decision surface that tells us what region is vowel number 1 versus 2 versus 3 versus 4 and so forth. Whereas if we used logistic regression on this, we would have literally a line somewhere. Well, I guess we wouldn't use it for, I have to step back. When I say that logistic regression has a linear decision surface, what I mean is if y that we're trying to predict, the variable we're trying to predict, is Boolean valued, then it will be linear. Of course, if we use the more general version of logistic regression, say with the softmax function, then what we'll get is a set of piecewise linear decision surfaces. But again, here you can see it's very curvy, not linear. Okay, so here's another example. It's one of my favorites because it's an early CMU example. This is due to Dean Pomerleau, and actually was his PhD thesis in 1993, where he was an early researcher in autonomous driving vehicles, and he simply trained he trained a neural network to take as input an image that the camera in the windshield is taking as the car is driving. He turned that image into a 30 by 32 grid of pixels, just like we could do with the Hillary photographs. And he trained a network which is 2 layers. Each circle here indicates 1 unit in the network. So this unit, for example, has 960 inputs, 1 for each pixel in the image. And this unit is a different one. It also has the same set of 960 inputs. And from each of those inputs, they have a weight which gets trained during the system training. And so this network structure, which we'll see quite often, is called I guess in this case we call it a 2-layer network, because there's 1 layer of units here, which look directly at the input, and there's another second layer of units here, which are the output, but they look not at the input image, but instead at the output of the first layer. So this would be called a 2-layer neural network with complete connections, completely connected in each layer. So each of these output units gets as input all 4 of the hidden units as input, and each of these gets all pixels in the image as input. So if you add that up, you can see there are quite a few units and quite a few connections between them. And again, here, this network was trained to steer the car, to tell whether the car should steer straight ahead or sharp left or sharp right. And again, initially, Dean used a 1-hot encoding for this. So if the training data, which was collected by letting Dean drive the car, revealed that he had turned this direction a little bit left, then that would be encoded as, here's the image that Dean saw when he went this direction. It would be again 0, 0, 1, 0, 0, 0, 0, 0. Later he changed that encoding a little bit to get it to generalize better, and but roughly speaking, that was how he started. This plot over here is also quite interesting because what this is showing is for one of these hidden units, it's showing the set of weights that were learned to go into that from each of the pixels in this image. And so here there are, I guess, 30 times 32 spots corresponding to the 30 times 32 weights going into one of these hidden units. And after the system was trained, you can see that it was putting a lot of weight, positive weight, that's what big white means here, positive weight on this section of the image. And black means big negative weight, put a lot of negative weight here. So if the image was bright here, then that would correspond to a high intensity being multiplied by a big negative weight. Whereas if it was bright here, it would be multiplied by this weight, giving it a big positive. Anyway, this is just a weight diagram. And so you can see it's weirdly road-shaped, but not obvious quite what it was doing. Yes? Yeah, I'm getting a little bit ahead when I say the weights, because we haven't really talked about the structure of these units, but that's coming up very soon. Yes? Yeah, it really was the first successful work doing this. Before Dean did his work, there was probably a decade, at least a decade, of people looking at self-driving vehicles of different types. But again, people didn't have the idea that machine learning could help. So they were writing algorithms. And a lot of that initial work happened here at CMU. And in fact, at that point, they had succeeded in getting robots to drive around in Shenley Park at about 10 miles an hour. That was kind of the state of the art. By the time Dean finished his work, he was driving on Route 28. I don't know if any of you drive up there, but Route 28 going out of Pittsburgh is a pretty busy road. He was doing experiments where his car was driving 60 miles an hour on Route 28. So it was, again, a huge leap forward just to go from trying to manually engineer these programs to instead training a system to do it. I should point out, he did most of his experiments at 7 a.m. on a Sunday morning, so the traffic was not so bad. Okay, and today, of course, a lot of the consequence of the last decade of research in deep learning is that we now have, for example, human level or near human level performance in speech recognition as well as computer vision in a variety of domains. And when I say speech recognition, I mean going from the sound to the text. I don't mean going from the sound to being able to answer the question. That's still far off. We also have things that 10 years ago I never would have predicted, like neural networks trained to assign words to pictures. So that can map from images to text. And in many cases, those do quite well, but not in all cases. So I don't want to give the illusion that neural networks are perfect. And Okay, so now down to details. So hopefully that kind of helps communicate why I'm very enthusiastic about deep networks. So these are built out of, as I mentioned, a collection of units. So for example, there's our old speech recognition network. That one happened to be built out of units that look like this. And this should look very, very, very familiar to you, because the units take as input x1 through xn, and they produce, each unit produces an output, let's call it O, and that output is computed in two stages. First, there's some weighted linear combination of x1 through xn. Oh, and also the bias term, like an additional input that's assumed to be always 1, so that we can have a weight on that as well. If you think about linear surfaces, having a x0 term up there that's always 1 gives us a chance to make linear surfaces that don't go through the origin. Right? So it just gives a little more flexibility on where the lines go. But then that linear combination of the inputs gets passed through a sigmoid function and outputs the result. So the reason that, of course, this should look very familiar is it's exactly the logistic regression functional form. And so the kind of surprising thing is that each of the units in that network is a logistic function, just like the ones you're training in your homework. Only now we have a whole network of these logistic functions. And so it's kind of a mind-boggling thing to say, well, what could that mean? We were very careful when we derived the form of logistic function to explain that we could think of it as being trained to estimate a conditional probability distribution. The output of the logistic function is P of y given the input x. But now if we have a whole network of these things, what does that mean? And when people were first experimenting with this, that's exactly the way they thought of it. They thought, well, there's no connection here to probability, but it works, so we're going to do it anyway. But as we'll see before the end of lecture, it actually, these days, we really do understand that these networks can be interpreted and used to train conditional probability distributions, just like we can use logistic regression to do that. So we'll see that today. Also, I want to point out, because we're going to use it a little bit later, something that you may already know, but one of the nice things about this sigmoid function, which is applied to the linear combination, is that there's a very nice formula for the derivative of this function with respect to x, which is just that it's the output of the function times 1 minus the output of the function. So that's a handy thing to know. We'll come back to why. Okay, but that's not, these days there are many kinds of units that deep networks are built out of. One of them is the sigmoid function. But for example, there's another very popular kind of unit that people put in networks that is called a rectified linear unit. It looks a lot like the logistic function, the sigmoid unit. Again, it takes its inputs and has some weighted linear combination of them. But instead of passing that through a smooth sigmoid, it just passes it through this very simple nonlinear activation function. We often call the second half of these units the activation function. And so you can say that, you know, if my input here is the x dimension on that plot, then the output is just either 0 if x is negative, or its input. If I shouldn't have said x, I should have said net. If the horizontal axis here is net, that's the symbol I was using for this, then it's either outputting what was the input, or if the input's below 0, it outputs 0. So you can see both of these are ways of making units whose output is not a linear function of the input. And in fact, there are plenty of other variations and different types of units that are now used. Yes? Sorry?
What do you mean by a unit?
A unit is just a computational unit. This would be one, that would be one, that takes some inputs and then computes an output. And these inputs are, each of them is just a single real valued number. Could be, we can make them Boolean if we like, but as far as the network's concerned, they're real valued. And it outputs a single real valued number.
The output is a unit?
No, the unit is this whole computational unit. So I would say these are the inputs to this unit, and this is the output of the unit. And it turns out in both of these cases, what gets learned when we train the network are these parameters, the weights on these inputs. Everything else is fixed. It's just like logistic regression, right? You assume this functional form for logistic regression too. And when you train your logistic regression, the only thing that gets learned are these weights. And so it's the same with these units. Okay, and often you'll hear people talk about the activation function that they're using for their units, and often many of these units calculate their output in a two-stage process, like logistic function does, where there's first some computation, and then that leads to a single value, which is then passed through some kind of nonlinear or linear activation function. So you can think of each of these units as really the composition of some f with some g of x. And not in all cases, but in many cases, this is what the design of units look like. And you will see terminology like people talking about the activation function. They really mean this thing that you pass the first part of the computation through. Okay, so now I have to tell you there are many types of units. We'll go through some of them in this lecture and next lecture. But for example, we talked about the rectilinear unit. This is one way to set it up. A second way to set it up that people sometimes use is to make the slope in the left part of the curve, instead of just having that be 0, have it be slightly negative slope. And furthermore, to put a parameter there so that you can train the magnitude of that slope. And so there are all kinds of variations on these things. What's important, and if you want to boutique design your own unit, you may, but it turns out that what's important is that your unit, in order to be trainable with the usual methods for training deep networks, needs to have two properties. One is the output should be differentiable with respect to the inputs. And second, the output has to be differentiable with respect to each of the parameters that are learned. So not just the x inputs, but also the w parameters. And you can make up pretty much any functional form you like with any parameters you like, provided your overall unit satisfies those two properties. The output should be differentiable with respect to both the inputs to the unit and the parameters. Now you might say to me, wait. This rectilinear unit does not satisfy that because the derivative in some cases is 1, but in the other case the derivative is 0, but at this one point the derivative is not really defined. And you would be right. But we get away with it anyway because it's almost everywhere differentiable. And in practical terms, that's good enough. And so what people do if they need the derivative, and they happen to have this situation where they're right at that one point where the derivative is undefined. To its left, the derivative is 0. To its right, the derivative is 1. What they do is they randomly choose either a 0 or a 1. Okay? But so you're in good shape if it's differentiable everywhere. Practically speaking, you're even in good shape if it's differentiable nearly everywhere. Okay, and the reason that that's an important property of the units is that our training procedure is gradient descent, just like it is for logistic regression. And so we have to be able to calculate those derivatives in order to train our system. Okay, we'll come back to some of these over the next few lectures, but just to give you an idea, the max pool unit takes a set of inputs and it simply outputs the biggest input. The LSTM unit, which stands for long short-term memory unit, is a much more complicated looking unit that's actually built up out of several other things you might recognize as sigmoid or rectilinear units. But it's still a computational unit that acts as a memory. If you have a sequence of inputs like in a speech system or a video or a stock market prediction, then you might want a memory somewhere in there to keep track of important things that happened in the past. And LSTMs are a type of macro unit you can think of that act as memory. And in fact are also trainable to decide so that they can learn to determine what to remember and when to erase it and when to overwrite it with something else. Okay, so there seems to be a very active process these days of generating interesting, useful units and also experimenting with them to see in practice whether they help. Okay, so if you want to train a deep network then, here's what you have to do. First, just like everything else we've talked about in this course, you have to begin by deciding what is the function you want to learn and what is the objective you want to optimize when you train that. And mostly in this course, we've talked about two objectives, right? We might want to train to the objective of maximizing the likelihood of the data. We might want to train to maximize to make the parameter estimates the most probable given the data plus some priors on those. We talked last lecture about a way of thinking about linear regression, where we showed that if we wanted a maximum likelihood estimate of the parameters for linear regression, you can think of that as simply a linear unit with inputs and the output of some weighted linear combination of them. Then we talked about how minimizing the sum of squared errors between the predicted value, h of x, versus the true value, y, and minimizing the sum of squared errors we talked about last time could be equivalent, if we make some assumptions, to getting the maximum likelihood estimate. If we assume that the data we're looking at has zero mean Gaussian noise added into the y values. Now, one thing we cannot do is use what people call 0-1 loss. We've talked about that. In fact, when we talked about decision trees, that was kind of what we were after, was maximizing the classification accuracy. Although if you think carefully about decision trees, they don't do anything explicitly to guarantee that they'll maximize the classification accuracy. But that's actually not a good function for training neural networks, because we also need the network activities and parameters to be differentiable with respect to our loss function. And this is a discrete function. If you go back to that network that was predicting which vowel sound, ah or ah, somebody is making, it turns out that the loss function, you can change a lot of parameters continuously and not change the accuracy until you change them just enough to flip the label of one of the examples. And so those derivatives are kind of zero in almost everywhere. And then there are these step functions where the parameter gets adjusted to some value where it suddenly changes. So 0-1 loss is actually not a very good thing to train. We don't want to just count the number of mistakes and minimize that, because it's not a smooth function of the inputs or of the parameters. Okay, so step 1, choose a loss function. Step 2, design the network architecture. Decide what kind of a network structure you want and what kind of units you want in there. And there's plenty of art here. This is not always a science. Although when we talk about convolutional neural nets next time, you'll see that there is sense to why people choose particular kinds of network architectures for particular kinds of application. And then we want a training algorithm. I can't believe I left E hat in there, because I'm using J of theta to represent the cost function here. But then we want to derive our training algorithm. And just like the case of logistic regression, what that mostly means is finding the gradient. That is, the derivatives, the partial derivatives, of all of the parameters of the network with respect to our loss function J of theta. And then choose a gradient descent, an algorithm that will do gradient descent. Then choose a gradient descent method. And as we've talked about before, you know, there are gradient descent methods that, for example, use all of the training examples to calculate the gradient and then take a step. And then there's variation called stochastic gradient descent, so as we've talked about, that, for example, just compute the gradient with respect to each individual example and take many more smaller steps. And which one of those you want to use is a function of two things. One is computational cost, because training some of these networks can be very expensive if they're large, if they have millions of parameters. And second, generalization, how well they generalize beyond the data. And it turns out there are gradient methods, we'll talk about a few of them, like dropout gradient method, where you sometimes ignore or pretend that some of the nodes in the network aren't even there, for example. So you do a kind of randomization of the gradient descent method by doing that. Or things like momentum, where you remember the gradient step that you took last iteration, and you try to keep going in that direction, even if the new gradient's in a somewhat different direction. So there are a lot of engineering attempts to make gradient descent work well in neural nets. And again, the two drivers on that are the computational cost can be quite high for training, and also you want it to generalize well. And unlike logistic regression, we talked about logistic regression in class and pointed out that it has this nice loss function with just a single minimum, or if we're trying to maximize the data likelihood, there's just one maximum. So if we get to the top, we know at a local top, we know it is the global top. But in neural nets, you have very complex, multimodal, our loss function j of theta will be some very complicated function of all of the parameters in the network that make up the theta vector. And so there are many local minima. That's the second driver on research toward developing variants of gradient descent to try to handle the multimodal, multiple local minimum problem. Okay, so I want to, from here, primarily what I want to do is an example together, because I think the right way to really understand this stuff is for us to boutique design a particular network and take it all the way through. So that's my goal. I want to use this as the target function that we're going to design a network for. My function has just two inputs, Boolean x1 and x2, and just one output, which is a Boolean y. I want to learn p of y given x1 and x2. And here's the secret target function that I have in mind. Again, x1 and x2 are Boolean, but if they have the same value, then with probability 0.9, I'm going to output a y equals 0. And how often will I output y equals 1 in that case? 0.1. 1 minus that. So I didn't have to write down that term because you would just infer it. But if they're not equal, then I'm going to output y equals 1, also with probability 0.9. Okay, so you could think of this as a kind of probabilistic version of an exclusive OR. Right, exclusive OR, if I have two inputs, the output of an exclusive OR function is 1 if either one of my inputs is input, is 1. But if they're both 0 or if they're both 1, then the output is a 0. So this is just that, but probabilistically. So in my training data, I'll just say that 90% of the time my training examples will, in this case, will output a 1, and in the other 10% they'll output a 0, even if this holds, and similarly there. Okay, so it's a probabilistic, non-deterministic function I want to train. And why wouldn't we just use logistic regression? Right, this is not a linear decision surface kind of problem, right? Think of the, maybe I should flip this down so I can draw in a more sane way. Okay. Yes. Okay, so x1 can be either 0 or 1, and x2 can be either 0 or 1. And then they can, so there are really only 4 possible inputs, right? x1 and x2, both 0, both 1, or whatever. Okay, but I'm going to, if I take the non-probabilistic version of this, I'm going to here say y equals 1. I'm sorry, y equals 0, y equals 0, y equals 1, y equals 1. And so the problem is you can't really, there is no linear decision surface that'll get this correct. Right? I could try this and say, well, on this side I'm going to say y equals 0, and on this side I'm going to say y equals 1, but that won't really work because it'll get these two right, but it'll get that one wrong. So there's no way to actually put a linear decision surface in here and do the right thing. Okay. All right, so that's our problem. And so here's what I want to do. I still want to train a probabilistic function, and we will. But obviously, I need something more complex than logistic regression. And so I propose the following network architecture. Let's make the output of our network, here's our output, a sigmoid unit, because that's what logistic regression uses. Actually, I'll do it this way. And it'll be a function of two inputs, but those inputs are not going to be x1 and x2 because, as you already showed, we won't be able to learn this complex of function. So instead, what I'm going to do is I'm going to have x1 and x2 be inputs to some other units, and those units are going to have to compute two features that have the property that our sigmoid unit can, in fact, get the right probability. So you could think of this two-stage network as this stage, which is a lot like logistic regression, because it's going to use sigmoid units, logistic units, is going to be operating on pre-processed versions of x1 and x2. And this part of the network, if it trains itself correctly, is going to have the responsibility of finding some transformation of the original x1, x2 variables into a different pair of variables such that logistic regression can, in terms of those variables, find a linear decision surface that does the right thing. And this is a very good way of thinking about, again, why neural nets are so important. It's sort of like we can take everything that we said about logistic regression and just prepend to it a pre-processing stage, where that pre-processing stage basically is being trained to learn some re-representation of the input such that we can learn a probabilistic function, which is a linear decision surface in this transformed space. All right, so that's what we're going to do. And to be more precise, here's my proposed network drawn a little more carefully. So again, the input is going to be x1 and x2. I'm going to use superscripts in this case to represent the different layers of the network. So this is a two-layer network. Layer 1, or input stage 1, has two Boolean values. I can think of that as a vector x superscript 1 vector. And it has 2 units in the hidden layer, which then go to a sigmoid unit. These I'm going to make rectilinear ReLU units, which again have the property that the output of each, so there are 2 units, this one which depends on both inputs and the other one I can't reach which depends on both inputs. And both of those have the same structure, that is their output, f2 of g2 of x, will be some function f2 of some function g2 of the inputs. And g2 is just going to be a weighted linear combination of the inputs. And then we're going to pass that through that sharp nonlinear activation function, which either outputs what comes in, or if it's negative, outputs a 0. And then the second stage, the sigmoid unit, is going to simply be what a logistic regression style unit, which again first takes a weighted linear combination of its inputs and then passes that through the sigmoid function. Okay, so now if I want to train this network, what that means is I have to find a method to estimate all of these parameters, right? The weights. I use B here to represent that bias term, the one where we remember in that one network we had just a constant one as an input to each unit so that we could learn the intercept of the line. And I'm also going to have to learn these parameters and these parameters. And those are all the parameters in the network. So I'm going to have to learn one set of these parameters for this unit and two sets of those parameters, one for this unit and one for that. Okay, so I would say this network has 3 units. One, this is the output of the first unit, the output of the second unit, the output of the third unit. And so, does it make sense? Okay, so now to get started, we want to come up with our loss function. And I want to just train it to do the same thing logistic regression would do. That is, I want to maximize the conditional likelihood of the y's in my training set given the corresponding x's that are in the training set. Same thing we did in logistic regression. We maximize the conditional likelihood of the y's given the corresponding x's. And for some reason, the convention in neural networks is to talk about minimizing instead of maximizing things. So what I'm going to do is, instead I'm going to minimize the negative of the log of the conditional likelihood. Okay, so it's the same thing. But I could either minimize this quantity or maximize the quantity without the minus sign in it. It's the same thing. I want to, over the different training example XY pairs in my training data, I want the sum of the logs, of the negated logs, so when the network outputs a particular probability, I want the probability that it outputs. This is going to be what the x super 3 sub 1 outputs is its estimate of this probability given whatever the input is. And I want that to, I want this function to be minimized where y is the actual observed value in my training data. So what if for a given x the output y is 1, I want this term refers to whether the output correctly predicts that y equals 1. And if instead y equals 0 in my training data, then this term will be based on the probability it assigned for y to be 0. And then theta, the set of parameters, is, as we discussed, that set of parameters. Okay, so this is really so far no different from anything we've talked about in our course. For weeks now, we've been talking about coming up with some functional form. In this case, we have a new functional form for the function that we want to represent, choosing an objective that we'd be happy with. And we've been generally happy with things like maximum likelihood, maximum conditional likelihood, map. And here again, this is basically a maximum likelihood objective. I want to make the observed data as probable as possible according to the set of parameters that I'm estimating. Or in neural net jargon, I want to minimize the negative of the likelihood. And I'm taking the log here for the usual reason it makes arithmetic easier. Okay, so now how are we going to train this? This is where it starts to get interesting. And I propose we do this on the blackboard because there's going to be some derivation involved. But let's just start now. So our job, we've picked a neural network structure. It has a set of parameters. We want to develop a training algorithm. And again, all that means is we're going to use gradient descent to train this network. So to develop the gradient descent algorithm, all we really need is the partial derivative of our objective function that we're trying to maximize with respect to each of the parameters of the network. Because that's what the gradient is, right? It's all those partial derivatives. We calculate them, and then we take a gradient step, and we recalculate them and go. So we're going to do that, but I want to point out that our loss function, which again is the sum over all the training examples of the log of the correctly assigned probability mass negated so that we minimize it. I can write it this way. We've talked about this before, but I want to remind us because it's going to be important. This expression is completely equal to saying to this expression. Here I'm just adding up the log of the probabilities of the correctly assigned probability mass. Here what I'm doing is the same thing, only I'm using the fact that y can only be 0 or 1. If on the kth training example y sub k is 1, then I'm going to have this term, and this will be 0. So if y equals 1, I want to add in the probability that my network assigned to y being 1. On the other hand, if y equals 0, this term will be zeroed out, and I'll instead choose the probability that it assigned to y equals 0, which of course is just 1 minus the probability that y equals 1. Okay, so this is our old friend, the if statement written in algebra. Okay, so I'm going to start here. No, let's just go to the blackboard. This will work better. So let's see. I can turn this. I don't want to turn the whole system off, do I? Do I? Shall I turn the whole? I want the screens to go up and the thing to go off. Oh, blank. Oh, that may even be better.
Do you want it just on one side?
Yeah, let's do that because now I can leave this up. And we can look over here. Oh, can I do it the other way? Because I know that one's empty. And besides, these lights are on, so this is good. Thank you so much. Okay, this is great. Whoa. Okay, now we've got lights to it, so we're in great shape. Okay, so here's... Let's do it this way. Okay, so what I'm going to do is I'm going to draw our network with some just schematically. Oh, wait a minute. Let me make these big enough that we can see. So this is meant to look like the one we're already looking at over there. And here's what I'm going to do. I'm going to say, I'm I'm going to make a little table down here where we can say what the inputs are for x1 and x2. Let's say this is going to be, what do we call that, x11 and x12? Yes. So x11 and x12. And I'll give those some values. Let's say we're going to input a 1 and a 0. So what I'm going to do is first, let's initialize our network with some random weights. And then we'll calculate the output of the network, given those random weights. And then we, in the training pass, we're going to have to calculate the gradient. That is the derivative of our loss function, the negated log likelihood, with respect to each of these parameters, and then take a training step to update the weights that started out to be random. So that's one step of gradient descent. Okay, so suppose that I start out, let's see, we need, on this part, for each of these two units, we need basically the parameters that are the linear combinations. And then I guess f, the max function, doesn't really, that rectilinear threshold thing doesn't really have any parameters to learn. But what I want to do then is just, let's compute what the output of the, so here's my input. Then I'm going to have a set of weights, the B's and the W's. And I have two sets of these B's and W's, one for this unit. This is the, and one for this unit. So let me just say this way. These will be for the unit whose output is this one. And these will be for the other one. And this has to be a linear, we have to compute some linear combination of these. So we need weights. How many weights do we need here? 2, right? We have 2 inputs, we need 2 weights. And we need a constant too. Something to, you know what, here's what I'm going to do. I'm just going to say this is a frozen 1. You cannot change this 1. But it'll, now what I want to say, the sum of wi xi plus b, I'm going to rewrite that as the sum not from 1 to 2, but from 1 to 3 of, and I'll just pretend this is the shadow. I'll just fake that there's a third input, which is always 1. It'll just make it easier for us to keep track. See what I'm doing? So I'm just going to pretend my weight, that I have 3 inputs. One, two, three, and that's weight 1, weight 2, and the constant. That's the way we're going to learn on this constant one. Okay? Okay, so that's what we need to compute. What are we going to compute from that? From that, we'll be able to compute G2, right? That's the, for these rectilinear functions, remember, we take some inputs and then we pass it through the rectilinear function and output something. So I'm going to call this G. And I'm going to record what that is. How many G's will we have? 2. Right. 1 for this unit, 1 for this unit, and then we'll have an output, which are my x's. So this will be x2, And of course, there are two of those, this one and this one. Okay? Okay, and now similarly here, what does the sigmoid unit look like? Well, it looks just like this, except it has a smooth function here, the sigmoid function. And so what I need here is also, let me add that immutable 1 here again. And then I'll do the same thing here. Now, how many weights do I need here? I only have one unit this time, so here I have one for the top unit and one row of weights for the bottom unit. This time I just have one unit. Let me still get G, which is just the, Wx plus B. And then the output, which will be X3. Okay? Now, if you in the future, for example, in the next homework, have to hand execute a neural network, my very, very, very strong recommendation to make your life easy is to begin by doing exactly what we just did. Because now we know exactly every single quantity involved in this network. Some of them are data that is passing through the network. Some of them are parameters of the network. In fact, let's even distinguish them. I'm going to double box those, because those are actually parameters of the network, and so are these. In fact, those are the only parameters of the network. Everything else is just data we're computing, right? Okay, so now let's pick some random values to put into these, to initialize. If we're going to build a network, we have to just put some random values in here. Let me propose. I'm going to put 0.1, minus 0.1, and 0.1. And then for the next row, I'll use minus 0.2, and 0.1, and 0.05. Okay. And over here, I need to put some also. Let me use 0.1, 0.09, and 0.1. Okay, usually, in fact, if you train a network or a logistic function, it's fine to just start with small random values and let gradient descent take care of the rest. Because these are the parameters that are going to get updated every time we do a gradient descent step. We're going to update every one of those parameters. And in fact, I propose that for our training, we do stochastic gradient descent. That means we just use one training example at a time. We will pass that training example through the network, having to calculate these intermediate things. And then we will look at the training example value of the output and compare that to what the network outputs, compute our loss function, and have to get the derivative of that loss function with respect to each of these parameters. And then once we have that is the gradient, then we just update each parameter by adding in some fraction of that, the learning rate, some fraction of that gradient. So we'll move each of these parameters in one direction or another, either up or down. Okay? All right, so let's go forward. Since I've proposed that we use 1 and 0 as our first training example, what now is the value of G for this unit? Again, G is just the weighted linear combination. So that'll just be, oh, look, I can do matrix algebra on this. It's very easy. I can take this column vector, multiply it by the weights that are associated with this, And I'll get, so it'll be 1 times this plus 0 times this plus 1 times that. That looks like 0.2. My notes reveal that's correct. Man, okay. And then for this one I have what? Minus 0.2 plus 0 plus 0.05. So I guess it's minus 0.15. Right? Okay, so that's what we get in our rectilinear unit right here. For the top rectilinear unit, the value here is 0.2. For the bottom one, it's minus 1.5. And so what are the outputs? What's the output of the top rectilinear unit? It's just the max of 0 and it, so it's outputting a 0.2. This one, however, since it's negative, the max of 0 and this is 0. Okay. Now we have the inputs for the second unit. That's easy. It's just this vector dot product with this. So 0.2 times 0.1 is 0.02 plus 0 plus 1 times that looks like 0.12. Okay, and then, did I get that right? Yes, okay, and then, so x3 is now what? Oh, this takes passing it through the sigmoid, which I've done in advance. So this gives us 0.53. Okay. All right, good. The network is done making its prediction. What is the prediction? What is it predicting? Right. This is its prediction that the probability of y equals 1 given that x equals the vector 1, 0. Right? Given a 1 and 0, we're treating this output as that probability. So it's predicting it's slightly more probable that y equals 1. Okay. Now for the exciting part. How are we going to compute, now that we've done this feed forward and we've saved all these values, oh my, we're going to run out of time. Okay, so let's throw away the notes. I'm going to take a picture of this and we're going to resume next time. But you're probably thinking to yourself, man, it's going to be murder to get all those derivatives. It's actually not. It's going to be trivial because we are saved by the chain rule of calculus. The parameters we need are, what do we need? We need the derivative of our loss function, that's the likelihood, with respect to this, with respect to these 9. I guess that's it. There are 9 parameters. We have 9 derivatives we're going to have to derive from this. And you know that loss function was that thing we looked at before. Oh, there it is. There's our j. So we have to get all those derivatives. But here's what's going to be beautiful. What I'm actually going to predict, or what I'm actually going to calculate, is the derivative of that with respect to x3. And then also with respect to g, and also with respect to this, and this, and this, and also with respect to this, this, and this. Oh, not this. Also with respect to this and this, and then these. And the reason I'm going to do more than we need is it'll make it kind of a dynamic programming algorithm. Because the chain rule tells us that if we want one of these, like let's say W31, which would be like W, I guess I'll call this W2 and W3, because these are in the computing the third level. So if I want the derivative with respect to this, for example, if I already know the derivative with respect to what comes before it, g, then all I have to do is this. So the chain rule tells me that if I want to know the derivative of our cost function with respect to any parameter, I can always factor it into two terms like this. And what I'm going to do is, first I'll get the derivative of the cost function with respect to this. Then the derivative with respect to this will be simply what I already calculated plus the derivative of this with respect to this. Now I have the derivative of the cost with respect to this. Now when I want it with respect to this, all I have to do is use the chain rule, as shown right there, to use the fact that I already know this term, and all I have to get is the derivative of this with respect to this. And similarly, all the way down the line. So what we're going to do is compute a sequence of derivatives that goes the partial derivative of j with respect to x3, then we'll get the derivative with respect to g3, then we'll get, because it'll just be that little incremental computation, then we'll get it with respect to w and all the little wi's, then we'll get it with respect to x2, and each of these in turn will require just a little minuscule derivative. Furthermore, we'll know the values because we have the values of all these things. And so that is, in fact, the backpropagation algorithm. That's why it's called backpropagation. Because the way we calculate the gradient is we take basically the derivative of our output with respect to the cost function, and then we propagate that derivative back by just incrementally computing all the derivatives. So it's fairly efficient. All right, I'm sorry we ran out of time. I guess I got carried away with my enthusiasm for neural nets, but we'll make up for it next time.